So the spectral theory, the spectral theorem for symmetric operators is a very important thing. Another important thing are the Fredholm alternatives. And Fredholm alternatives is again something you might have heard in talks, or you might have written in, you might have read in papers. People just talk about Fredholm alternatives, and many people have actually very different ideas about what a Fredholm alternative really is. In fact, in this section 7.4, we will find 3 versions for the very same. No, not very same. We find 3 versions which are all a little bit different. The key here is to have operators of finite rank. So a linear operator, let's start here. A linear operator has a finite rank if its range is finite dimensional. Okay, and then finite rank operators have a beautiful spectrum. If A is finite rank on a Hilbert space, and if for lambda non-zero the infimum of A minus lambda Ix in the norm for all x equal 1 is 0, then lambda is in the point spectrum. So let's prove this. We consider a sequence xn in H which has norm equal to 1. So that this infimum is 0, so that the limit of A minus lambda Ixn goes to 0 for n to infinity. Now, since the range of A is finite, there exists a convergent subsequence in the range of A. Just Bolzano-Weierstrass. So then Axnj minus y goes to 0 for n to infinity. Convergent subsequence. Next page. So then I can write these xnj in a funny way. I write them to be 1 over lambda, lambda I minus a applied to xnj, plus a to xnj. Okay? If you ignore the under braces for now, the a terms cancel, the lambda cancels, and you get xnj back. But now looking at the under braces, the first term, lambda I minus a, xnj goes to 0 as xnj was chosen exactly this way. And then Axnj converges to y because we have a convergent subsequence. So then all this converges to 1 over lambda times y. And looking at the norm then, this norm of xnj converges to y, which is then 1 over lambda times y. And now we apply this to a. So Axnj converges to y. And it converges to 1 over lambda ay. Where does this come from? Oh, this comes from earlier. Yeah. So then this implies that ay is lambda y and lambda is an eigenvalue. So this means corollary 742. If H is a Hilbert space, A is a linear map with finite rank, then then each lambda has 2 possibilities. It could either be in the resolvent set or it could be an eigenvalue with finite multiplicity. Okay. So let's assume lambda is not an eigenvalue. Lambda is not in the point spectrum. Then by the previous proposition 741, a minus lambda ix cannot go to 0. So the infimum of that is not 0, which means it is bounded away from 0. So there's a c, so that a minus lambda ix is larger or equal cx for all x in H. Now let's consider another point y in the range of a minus lambda I closed, which means we can approximate it with points xn, so that a minus lambda I xn is approximating this point y. So then we look at xn minus xm, and we want to show this is a Cauchy sequence. So by the previous estimate, by this one here, we can estimate xn minus xm to be 1 over c a minus lambda I xn minus a minus lambda I xm. But now the a minus lambda I xn and a minus lambda I xm, they both converge to y, so this is a Cauchy sequence. And the limit is, which has a limit in h, which we call x. So then a minus lambda I x will be equal to y, which means the resolvent R lambda A exists. So then the range of a minus lambda I corresponds to the domain of the resolvent. Okay, so for each element in the range we can find the inverse. And so then, and the limit point is included, so then these sets are closed. And as lambda is not in a point spectrum, then it's also not in the point spectrum of the adjoint. And then we use the relation between the null space of the adjoint and the range of the operator in this form. So the range of a minus lambda I is the kernel of the adjoint operator a minus lambda I adjoint, orthogonal, but then this must be the entire space. Because earlier we did this for all x and h, so right for here. So, one more step. So now we define an operator t, ty, that's a unique element x, so that a minus lambda I x is y. Okay, so this t looks funny, but it is really the inverse of a minus lambda I in disguise. Because now we can compute a minus lambda I ty, so that being unique ty is equal to x, and then a minus lambda I x is y. And we can estimate c of the x norm, which is c times ty, is less or equal a minus lambda I ty, which is equal to the norm of y. So then this operator t is bounded, and in fact it works like the inverse, so it is the inverse, a minus lambda I inverse, and lambda is in the resolvent set. Yeah, finally, if lambda is in the point spectrum, then the eigenspace must be finite dimensional, since A has finite rank. Yeah, I'm not quite sure how this works to narrate these proofs. It is a little bit, I don't know, I'm not quite satisfied how this works. But you have the notes here, so maybe you really need to sit down and go through it step by step. And if you have questions, you can always ask me. So, here the important part is finite rank. And then we have either point spectrum or we have resolvent. So it's basically the part, it's basically the case of the reals, like we have it for matrices.